Hello, everybody. So my name is Sven Schage, and I'm going to present you an overview on basically the stage of the analysis of those algorithms, and especially where like TOE has been involved so far. So I have not been personally involved in analyzing each of these schemes, but I tried to give a good overview of what has been done. After that, like Alex is going to give a very interesting technical talk, which contains a very recent analysis of REDOG. Okay, so I'm happy to be here, and let's jump right in. Okay, now, well, so first of all, I mean, this is like a competition with an ongoing process. So we are analyzing schemes in sometimes in their first version, but also for updated schemes. So I know that for a lot of schemes, updated parameters have already been proposed, and we are aware of them. And we will still analyze these schemes, but I mean, like this is going to be a very general overview and also focusing on stuff that has been done, right? So so any result that is in here does not mean that we don't know that there are updated parameters, and we will try to look to have a look at them as well. Okay. Now, so yeah, what is basically our approach here? So we study the submission documents. We identify the mathematical hard problems that the schemes are based on, right? And for some schemes, they are more formal in the sense that there's something like a security reduction. For other schemes, like this is like more experimental than like traditional cryptography. These like security arguments are more loose than a security reductions. But anyways, we analyze that from the documents, and then we have a focus on three things. So the first one is like we estimate like the underlying mathematical problem. So this is a new problem, then we try to make sense of that and analyze how difficult that should be, like in more general terms. Then we attempt to cryptanalyze the way the hardness of the system is linked to the hardness of the underlying mathematical assumption. So the one way to do that is like to read security their reductions on the one hand, but on the other hand, well, we might try to find some discrepancies between what is actually like the underlying mathematical problems, and maybe there are some attacks that could be launched against the system if there's no reductions in the sense, but which are not really covered by a mathematical problem. So it's also really about the combination and the foundation on these mathematical problems. And then we specifically check the security reduction, of course. Well, and if this like seems like a good reduction, if it like, and this is especially easy if it has more traditional arguments, of course, then this focuses our cryptanalytic work quite substantially, of course. Now, for the surviving submissions that don't like pass this first check, we also focus on efficiency, right? So in terms of sizes, of course, I mean, for signature schemes, one important size is, for example, the signature size, but also for other metrics like speed and bandwidth. And I mean, after that, we also have a look at what security, if there's a reduction, what that means in terms of concrete parameters. Because, well, security reductions, they can differ in how well the reduction actually applies to practical parameters. And that is also an issue that has gotten into the focus of the crypto community over the last years, much more. As I said, well, this is an ongoing process, and in this talk, I tried to give it an overview of where we are now. Okay, good. Now, so I'm going like through. I'm trying to go all through the through all the different primitives that we have analyzed, or other people have analyzed, and like they give some brief comments on that. Okay, so IPC is based on graphs. It's rather not like the traditional. It's based on new ideas, very interesting new ideas. It's not the traditional way that people have contributed in let's say the NIST competition so far, and that was very interesting. However, well, I mean structurally it is based on a dominating set, on the difficulty to find dominating sets in three regular graphs. So, and this actually looks like good and hard solid problem. And so from our perspective, however, like Bernstein, Koutaru, and Lange, they found an attack to extract the message from the ciphertext, and was published quite early and on 23rd of December 2002 at the forum. So very roughly, the encryption partitions the message into some summons, and each of these summons is assigned to a graph position. And encryption uses the graph properties to obfuscate these shares. So, and the main issue is that the resulting ciphertexts are very sparse. And I'd say that I mean for several of my comments, sparsity is a reoccurring theme here. In general, sparsity can, like, if we try as a developer of an algorithm, we try to exploit sparsity to save space and to reduce computation. But it turns out that in a lot of cases, they're reducing like sparsity or increasing sparsity rather this way. Too much is also dangerous. Okay, so but the main issue for KpqC is that the ciphertexts are very sparse and that the summons leak by frequency analysis in 90% of all the cases. Okay, and this attack has also been acknowledged so far. Okay, Entropy Plus. So this is already a lattice-based scheme using these three rings. So, and like choosing f in the specific rate as 3 times f prime plus 1 gives a faster decapsulation, but it requires logic Q. It uses a centered binomial distribution and hence has variable weight errors. So what we checked for was evaluation at 1 attacks, generics attacks, like including CFU combinatorial attacks and the golden collision attacks and reaction attacks. Our estimates so far do not always match those data in the summation, but we found no like serious attacks so far. We noticed that there has been a split of the Fujitake-Okamoto transformation, a transformation that is used by virtually all lattice-based chems so far, and like in general chems in general. That's the very popular transformation, and there was like something special of it about this, but we missed the CCA attack that was published by Joe Healy before, right? But I mean we were like quite close to that, so we can at least like confirm the attack and are waiting for details of the fix. And internally, well, our Fujisake-Okamoto transform specialist Hoffelmans had expressed concerns about the Fujisake-Okamoto transform as it is applied there. But we will check the new proof and the implementations if there is any, of course. Okay. Now, then there is like 2 more, I'd say more traditional schemes, Smaug and Tiger. And they are based, they are either on the module learning with error or module learning with rounding problems, or the ring analogs, ring learning with rounding and ring learning with error-based systems. Now, they both fit quite well into the template of existing provably secure lattice-based schemes. So they have like they follow quite a solid recipe so far. Very much like Kyber or Sabre do. However, they offer new trade-offs, and that makes them unique here. And also, I mean, they have the benefit of the recent developments so far, and they use these recent developments to further improve on their schemes as compared to something as Kyber, for example. While aiming at high efficiency overall for both these schemes, they optimize in different strategies. While Tiger is concentrating on meeting an upper bound on public key and ciphertext size, which in turn is like inspired by the payload constraints of IKey, of the IPsec protocols. SMARC specifically also optimizes for very small small sequence. So they have like, of course, they like have a wider goal set as well. But I mean, these are very unique features. I'd say. Bernstein pointed out on 28th of December, again in the forum, that these schemes might be they might suffer from the combinatorial attacks by Mai that was presented at KpqC, and this is basically a meet LWE attack with ternary secrets. And again, well, this is because these both schemes try to have relatively small sparse secrets. I mean, secrets either in the long-term secrets or either in the ephemeral secrets. So again, we are analyzing all the new parameters, and since the schemes are lattice-based as well, we of course also attack the same set of attack vectors that are true for and true plus. Okay, and specifically like generate attacks and reaction attacks. Okay, now the code-based chem. For REDOG, we are going to see the talk by Alex. A layered role 1 got analyzed by Chi and et al. in April this year already. So they were quicker than we do. And this attack has also been like acknowledged so far. And then there's also Paloma, which is close to the NIST submission of classic McAleese in using binary Gopper codes. But it seems to have some core differences. The Gopper polynomial G is chosen to split completely over this field instead of being irreducible. So this is something quite unique, I guess. The support and the two roots of G need to share, the same field. Hence, M is larger. And the authors, they generalized their Patterson decoding to this case. This looks correct so far, but it is slower than the Masai algorithm that is quite often used for similar purposes. This choice of G limits the key space, but the key space in like for the practical parameters is still very large. Okay, so we are still hunting for algebraic attacks using these G factors completely, right? So this is something that we kind of focus our attention on, as it is so distant from approaches where it is reducible. Okay, NCAPs and DCAPs are slower than and larger for classic McAleese. This is something to keep in mind, of course. And well, the proof analysis is ongoing, so the efficiency analysis suggests some changes here. And then there's AIMER, which is designed using the MPC and the HEAD framework. And as such, it is quite close to the NIST submission technique. The benefit of these schemes is that the security of the signature scheme relies merely on underlying the one-way function. Okay, the security model restricts attacker to a constant amount of data, and we were like specific. We are specifically interested in algebraic attacks here. since the security only suggests an upper bounds on the complexity of the attack. Okay. The experimental results suggest that the randomness is worse than what a linear congruential generator used in the C programming language should do. This is also something that is quite outstanding, I guess. So we are not really out of ideas yet, but we have not found an attack yet. Then there's FIPS. FIPS is based on the swings construction, but it uses isogeny-based hash functions, or a hash function that is based on the Charles-Goren-Lauter hash function instead of, let's say, SHA-2 or shake. So because of this choice, it is more than 10,000 times slower than swings with SHA-2 or shake. Okay, the sizes for swings are independent of the used hash, and therefore they are the same for the scheme as well. Okay. Yeah, so interestingly, these the analysis builds on the flawed proof stated in the first round submission of Swings Plus, and the AsiaCrypt 2022 there has been a fix of the proof, but it requires additional requirements on the used hash functions. Among others, it's not only something like the collision resistance, but we also need undetectability and decisional second preimage resistance as some of these properties. Further research is needed to understand if the used isogeny-based hash function CGL guarantees these properties that we need from the fixed security proof. Now, then there are the other signature schemes that we had a look at. So enhanced PQ-sign RM. There was a talk by Alex on the 17th of April. Then there was like GCQ, the GCQ signature scheme that has been attacked by Kim, Rio, and Lee. The authors promised some updates, so we postponed analysis of that. MQ sign, on the other hand, has been broken by Albach et al. I mean, it seems that the parameters for oil, for unbalanced oil and vinegar, still in general look okay. So there has been an attack on Peregrine by Espitau et al, and we are waiting for the updated parameters at this point in time. Okay, so now this should be like my overview so far. I'm happy to take questions on each of these points. But I mean, there's these, like, in general, to maybe say some words, like they are different chems and different signature schemes with like totally at times totally different, like for certain pairs, like totally different approaches. There's not so much that can be learned in general here. Maybe I think the one point is, as I said, is maybe the exploitation of sparseness. I mean, this is a common theme, and we would like to do that because we can save stuff. But it turns out that this seems in general to be a business one should be quite careful about. Okay. So thank you very much. I'm happy to take questions.
Okay, so I was saying that I'm going to present a little bit of work that I've been doing on REDOG, and contains also joint work with Tania Lange and Alberto Ravagnani. So REDOG is a code-based crypto system that uses rank metric codes. So to start with, I think I should give a little bit of background of what codes in the rank metrics are. So to start with, let's pick a basis of the field extension of FQ of degree M. Let this basis be alpha 1 until alpha M, so M elements. And then each element of FQ to the M can be written as a linear combination over FQ of these basis elements, okay? Where these capital Xi's belong to FQ. And therefore, we can just represent X as a M-dimensional vector over FQ. This representation can be extended to any tuple over FQM as the following math that takes any vector of length, let's say fix a length n over FQM, and it sends it to the matrices, m by n matrices over FQ. And it is defined by taking the ith coordinate of V, expanding it as we did before for X. I don't know if you can see my pointer. And then use it as a column vector for our matrix. And we call this the matrix representation of the vector V. Okay, so this is a matrix over FQ, and V is a vector over FQM. Basically, it's another representation. With this representation, we can define what's the rank weight of a vector V, and we define it as the FQ rank of the matrix representation of V. And from the weight, we can also define the distance between two vectors of FQM to the n. So still we fix a length. And we define this distance, the rank distance, to be the rank weight of the difference between the two vectors, or which is also the FQ rank of the difference of the matrices, matrix representation of the two vectors. Okay, so we're ready to define what the rank metric code is. So rank metric NKD code C is a k-dimensional subspace FQM linear subspace of FQM to the n, where n is called the length of the code. K is, of course, the dimension, and D is the minimum distance. And the minimum distance is defined as the minimum of the rank distance between two vectors, two distinct vectors of the code C. Okay, the correction capability of a code is defined as half the distance, -1, and we take the integer part of that value. So we define G to be a generator matrix of C if the rows of this generator of this matrix, they span the entire C, the entire space, and H is a parity check matrix of the code C if its rows, they span the right kernel of the generator matrix. As an example, Kapitelin codes are really well understood and well studied codes. Rank metric codes, they have a really nice distance, which is n minus k plus 1. And we also know efficient decoders that can decode up to the correction capability number of errors. So now already we have everything that it's needed for the specification of REDOG. This is going to be a little bit bulky. It requires a lot of data, so I will go through them, and don't worry about all the details. We are not going to need all of them, but just some chunks. Anyway, so as a setup, REDOG spits out a list of integers, L, M, N, K, R, T, lambda. All of them are needed to define the code. And L, for example, will be the dimension of the public code, and will be the length. So we want the dimension to be less than the length. And then we also want that lambda t, this is important, is less or equal than r, which is also set less or equal than n minus k over 2. This n minus k over 2 is gonna be the actual correction capability of the Kapitelin code that REDOG is gonna use. Okay, so before you saw the d minus 1 over 2, this is really gonna be the d minus 1 over 2 of a Kapitelin code. So this is the bulky key gen. For the key generation, we start by taking a parity check matrix. This should be H equal to H1 augmented with H2. A parity check matrix of a 2n minus k n Kapitelin code, where H2, the part H2 is invertible. It's an n minus k times n minus k matrix over FQM, and it is invertible. As you can see, the length the length of the Gabidal encode is 2n minus k, and the dimension is n, and therefore the correction capability turns out to be exactly n minus k over 2. And we set R to be exactly the correction capability. And of course, we also pick a decoder that can efficiently correct this number of errors. Then we pick a Nash function that takes tuples of 2n minus k symbols over FQM and spits out a digest, which is only L elements of FQ to the M. Then we take a full rank matrix M, which is an L times N matrix, and an isometry matrix P with respect to the rank matrix, and is an isometry of the FQM to the N vector space. And then this is what is the next point is what is going to be basically the nice addition that have been made in this new proposal of REDOG that distinguishes it from previous submission and proposal. REDOG chooses this matrix as inverse in the general linear group of lambda, where lambda is a smaller lambda dimensional subspace of over FQM. So basically, we take L linearly independent elements of FQM, and you can think of expanding them as a vector, as a matrix over FQ, and then this matrix is going to span a space, and all this space can be brought back to FQ to the M, and we have a list of elements, and we allow S-1 to have entries in these elements, I mean this space, okay? And it has to be invertible. So as a public key, REDOG has the two matrices M, so the full rank matrix L times N, and F, which is this huge composition of matrices that we just defined, okay? So we are not going to take care so much of this F, we're going to take more care about the rest, about this most lambda dimensional subspace. And as a secret key, we keep the isometry matrix, the parity check matrix. This H is exactly the augmented, I missed, it misses an H equal there. The matrix S, and also the decoder of the Gabidal encode. Encryption, when we want to encrypt a message, a message of length L over FQM using the public key, we generate a uniformly random error vector over FQM of length 2n minus k, and we represent it here as the concatenation of two vectors, E1 and E2, where E1 is of length n and E2 is of length n minus k. It sums up to n minus k, and we just REDOG just requires the rank weight of this error vector to be t. Okay. Then we compute m prime by taking the message and adding the hash of the error vector through our hash function that takes 2n minus k elements and spits out a digest of L elements. And then REDOG wants the ciphertext to be two pieces, C1 and C2. The C1, we encrypt M prime by M, and we add E1, and C2 we encrypt M prime using F, so the second part of the public key, and then we add E2. The decryption of this ciphertext, this two pieces ciphertext, using the secret key goes as follow. REDOG computes C prime to be this difference of the ciphertext modified by the isometry matrix and part of the parity check matrix of the private code, and also by this S-1 matrix that comes from that nice space of matrices. Okay, so this computation here, this modification is gonna end up to be exactly the syndrome using the Gabidal encode of this E prime error. Okay, this E prime error turns out to be the first part of the original error times the isometry, and the second part, the negative of the second part, the opposite of the second part, times this S-1 matrix, this special matrix that we were mentioning before. And yeah, it is claimed that this vector here has rank weight lambda t, and therefore it can be decoded using the Gabby-Doolin decoder. And so we can recover E, so the two parts of E, and then solve the linear system m primes times m equal to c minus 1 minus E1. And we output out, I mean, then we can take the, of course, once we have E and m prime, we can compute the hash of E, subtract it to m prime, and we get back m. I mean, I'm not asking you to completely understand what is going on here. I mean, everything is in the paper, and it's easily proven with some computation that it works. Okay. Okay. So what I found a little bit striking here is that how they can claim that this E prime is actually an error that can be decoded by the decoder of the Gabby-Doolin code. And in fact, I think I could prove that this is not the case, or almost never the case. And yeah, to do that, I came up with this nice lemma that says that if we take V to be a t-dimensional subspace over FQ to the M, okay, and we take S to be a randomly chosen, uniformly randomly chosen vector of S elements of V, then the probability that the elements of S are gonna span the entire vector space V is exactly 1 minus this big sum here. As you can see, this big sum here is gonna go very quickly to 0 when S grows. Okay, so S is the length of the vector that we take of elements of V, and this sum here is gonna go quickly to 0. So using this lemma, I mean, I can provide the proof of this lemma is quite nice. I will put it in the wrapper. Using the set of parameters that REDOG proposes, we can see that this is exactly the case, because for REDOG, for example, 128, we have that this t is 6, and this S is at least 36. Okay. And therefore, this is going to go very, very quickly to 0. And therefore, the probability of that lemma is actually very close to 1. And in this proposition, we use this lemma to prove that if we take a random vector, error vector E, like it is required in the encryption, then both of these two parts of E are going to have rank weight exactly T, when E has rank T. Okay, with probability almost 1. This probability almost 1 comes exactly from this formula, from this lemma. So what is in this slide? What this slide says is that if we take a random error vector of rank T over FQM, then both of the two parts will still have rank T. So recall that the E prime that appears in the decoding in the syndrome is made up like this. And then we have this theorem that sums up everything and says that the rank weight of E prime is going to be bigger than what they claim to be. Remember that they claim to have E prime with rank weight less or equal than lambda t, which is the correction capability in the end of the code. Well, we can prove that for a randomly chosen E prime has weight bigger than lambda t, with probability almost 1. I have some code that proves also this thing in an experimental way, but here I want to give also a sketch of the proof by using the proposition that I just gave. So using the proposition, we can prove that, of course, the rank weight of E1, this part here, times the inverse of the isometry matrix has, of course, the same rank as E1, because P is an isometry, so the inverse of P is still an isometry. And with the proposition, we proved that with probability almost 1, this E1 has weight T. We have we can also prove that the rank weight of E2 times S minus 1, there is a nice theorem from Laudreau in the paper they cited. And with probability almost 1, we can also prove that the rank weight of this part of E prime is exactly lambda T. And moreover, finally, we can also prove that the space generated by the matrix representation of the first part of E prime is very unlikely included into the space generated by the matrix representation of the second part of the error. And therefore, we can safely say that the rank weight of E prime is larger or equal than the rank weight of the second part, which is lambda T plus 1. And therefore, we proved the theorem like this. This is just a sketch. A more in detail proof is going to be given in the report. So as a remark, remember that phi, the decoder of the Gabidulin code, decrypts correctly, or decodes correctly, sorry, when the rank weight of E prime is less or equal than R, which is the decoding capability. We just proved that for a randomly chosen error, this is not going to happen. And therefore, this theorem shows that decryption of REDOG is incorrect, and the system is likely vulnerable to reaction attack. We still don't have reaction attacks on it. I don't even know if we can mount some, but we will still try. I think it's next goal. Anyway, this small almost 1 probability, of course, leaves out some cases. And one of the cases, one method to build errors that will work throughout the system is as follows. We just pick T elements of FQ to DM, which are FQ linearly independent, okay? We take also a random permutation of to n minus k symbols. We set up E init to be the vector of all zeros, where in the first T coordinate, we put in our T elements, which are linearly independent, and therefore we can just prove that this init here as rank weight T as a vector over FQM. And then we just scramble around this E. This, of course, has rank T, and this is gonna trick our theorem up there, because no matter how you put the elements, try to put all the elements, for example, in the second part in E2, and then you will end up that the rank weight of E prime is going to be exactly lambda T, or at least at most lambda T. So this is going to really trick the theorem. And this is exactly also how REDOG implementation generates its error. Okay, so, or actually in an equivalent way, but still this algorithm is going to show how REDOG creates the errors. Yes, and here is exactly what I said before, is that if you create the errors like this, then you have that your E prime is going to work, and it's not going to give decoding failure. But on the other side, there is another thing that has to be said, is that these errors, this algorithm creates errors that have Hamming weight equal to the rank weight, and therefore equal to T. The Hamming weight is just the number of non-zero coordinates of a vector, okay? And therefore, what we came up with is an idea, which is basically to use the public key, or the concatenation of the two entries of the public key, these two matrices here, as the generator matrix of a linear 2n minus k code over FQM in the Hamming matrix this time. So we forget about the rank metric, and we consider this code over the Hamming metric. And then we know that the error vector that is going to be added in encryption as Hamming weight T. We just showed it before. Of course, we are choosing it with rank metric T, but the weight of the error is exactly its Hamming weight. And so the idea is just to use information set decoding here to get back the error. And Prange is going to do exactly what we need. this is going to break the system by forgetting that it is a rank metric code. And we ran the attack on a Linux Mint virtual machine, and we broke all the KAT ciphertext for all the proposed parameters. For example, for parameters 128, we broke it in 8 seconds, 82 seconds for 192, and 232 seconds for the strongest parameter. The code is can be found in this URL. Okay, I also tried to patch the implementation because I saw that the implementation was using wrongly the randomness in Sage, and so I patched it in order to have really random values, and still we can break the ciphertext. Finally, we also believe that the attack costs in the paper have been computed incorrectly, because in all the costs formulas, the value of R is used. The value of R is the correction capability of the code. But during transmission, we have that the error vector has only rank weight T. And okay, T is just going to be R over lambda, where lambda is always set to 3. So yeah. But anyway, so I tried to plug in this T instead of R in the formulas, because I'm pretty sure that this is how the attack works. And then for example, for parameters 128, we find that the cost that has been computed in the paper are this one. As you can see, the most efficient one is the algebraic GRSH attack, and the recomputed cost is just 2 to the 34, and this can be really attacked on a laptop. An idea, of course, to patch up this thing and get back to the regional parameters is to increase REDOG's keys, but this is a little bit impractical because REDOG's keys are already quite large compared to any other code-based crypto system or rank metric code-based crypto system, and therefore this it's very unlikely to be the right way to do it. Anyway, as a conclusion, I would like to summarize what I've been doing. So I think we showed that REDOG's decryption is incorrect, and this is gonna expose it likely to reaction attacks, and therefore, yeah, it causes weak choices of the error vector in order to achieve this correctness. For example, these errors that have Hamming weight equal to the rank weight, and which is a low Hamming weight. And then we also gave an efficient message recovery attack on REDOG's implementation. And yeah, finally, we also think that the attack costs have been wrongly computed, and so we recomputed them. Then that's all. Thank you so much.